People, we're doing well. This one, as promised, we're going to be doing some converting back and forth between polar and Cartesian. But before we start, remember that how I described trigonometry and the fact that it's a mathematics of conversion, right? Trigonometry at its base is a way of taking language of outness and aroundness and translating it into up and down and back and forth, right? And of course, inverse trig takes you from the up and down and back and forth back into the realm of around, angle measurement, and out, radii. Okay, so with that in mind, it should not be a surprise that in order to convert things that are not just number values but equations, and of course all equations do is represent a set of ordered pairs that behave the same way, then we're going to use a certain set of conversion equations in order to go back and forth between polar and parametric. Okay, I'm going to have two examples real quick that I've already typed out. We're going to run through them real quick, and then we're going to do some examples. I'm going to run through some examples that are not sort of preformed. All right, we have x squared plus y squared minus 4x. Now, you ought to recognize the fact that that is a circle, okay? And all you would have to do is just rearrange the terms and complete the square, and you should recognize it as a circle. So what we need to do is we need to use these conversion equations in order to change this into r and theta. Well, I made it real easy because x squared plus y squared is obviously going to be r squared, and x right here is obviously going to be r cosine theta. And that's true, okay? And so if we group them like that, then we can take the x squared plus y squared and turn it into r squared, and take the x and turn it into r cosine theta, and then we can factor out the r. Now, when we factor out the r, what we're going to do is we're actually going to get rid of the r, because r is equal to 0 is just the pole. It's just that one point at the pole. And of course, this graph includes that point, because when you add 4 cosine to the other side, you recognize it as one of those circles from the last two videos, right? And basically, you can get rid of that r because that r is equal to 0 is already included here, of course, at specific theta values. Now, let's try to go the other way, okay? And here, this one's a little bit more complicated, but not much so. This is actually, it shouldn't, basically, it's the form of a conic section in polar. And so if we have that, let's go ahead and let's get rid of its rational structure. Does that sound good? I don't like it in its rational structure, and if I can, and you should be able to deal with rational structures, but if you don't have to, why would you want to? Multiply both sides by that denominator. We go ahead and distribute the r, and now I see that r sine theta right there. That r sine theta is going to become y, and that r is not squared, so it's going to become the square root of x squared plus y squared. At that point, I'm going to shove the 3y to the other side. I'm going to square both sides to get rid of the radical, and now I can recombine. I can distribute the 16 over here, FOIL that binomial over there, and then I can shuffle around the terms and combine them all on one side, and you should recognize that in terms of it's the rectangular form of a conic section. Alrighty, now let's go ahead and let's jump into ones that we will do together, okay? Alrighty, let's look at this. We have x and we have y squared. Alrighty, well, x, I know exactly what I'm going to do. X is going to become r cosine theta. And I know that y is r sine theta, so y squared is r squared and sine squared theta. Okay. Well, what I really need to do is I need to get r by itself, okay? And if I want to do that, I can basically work backwards from this. I can go, okay, if this were the end result of cross-multiplying, what would have been the proportion? Okay, we'll divide both sides by r and divide both sides by sine squared, and you're going to get cosine theta over sine squared theta and r squared over r. Okay, well, if that's the case, then let's go ahead and simplify this. Cosine over sine is cotangent, and 1 over sine is cosecant, and so this winds up looking a whole lot like that. Okay. Now, let's go ahead and look at this next one. This next one is going to be kind of the same thing. We're going to take the x, and it's going to be r cosine theta. We're going to take the y, and that's going to be r sine theta, and that's still going to be equal to 4. Okay. Now, if I basically multiply this out, I get r squared sine theta cosine theta is equal to 4. Now, I see the fact that I have sine theta and cosine theta, and if I wanted to simplify this a little bit, I could put a 2 right there, so long as I multiply the other side by 2, and make that r squared sine 2 theta is equal to 8, at which point r squared becomes 8 over sine 2 theta, or 8 cosecant 2 theta. Now, you can go ahead and take the square root of both sides if it's something that you want to plug into your calculator, but you would have to do both the positive and the negative. You would have to put the positive into R1 and the negative into R2, or of course vice versa. And this would be 8 over sine of 2 theta. Now, what's kind of fun is the fact that you recognize this as a transformation probably on the parent of reciprocal functions. So you know what that looks like. What you don't know, or which you may not remember, or I may not have mentioned, is the fact that that's actually a rotated. It's actually a rotated hyperbola. If you just kind of take it and rotate it 45 degrees, you'll see what I'm saying. Alrighty, let's go ahead and let's look at another one. Okay, we have 3x minus y plus 2, and we have, okay, so 3 r cosine theta minus r sine theta plus 2 is equal to 0. Okay, well, let's see actually what that does for us. If I want to get r by itself, which is always kind of a good idea because that way you can plug it into your calculator, you get r 3 cosine theta minus sine theta, and I'm going to go ahead and throw that 2 over to the other side, so it really is just a matter of division. And if you don't like that negative in the numerator, you can always put it down in the denominator and use it to flip that difference down there, and either one of those will actually work. Now, this one down here looks really, really nasty, and it actually kind of is. But what you need to recognize is that this is nasty when it's in rectangular form. When it's in polar form, it's actually quite easy. So, of course, we're going to take the x squared plus y squared, and we're going to make it r squared. And we're going to take this x right here, and we're going to make it r cosine theta. And this over here is 4a squared, and this x squared plus y squared is just going to be r squared. Well, once you do it that way, both sides are actually squares. Okay, so let's go ahead and square root both sides. To AR. Okay. Now, what I'm going to do now, and there's a reason why I didn't do plus or minus, and I'll show you that here in just a minute. Okay. I'm going to go ahead and divide through by r. Or, I mean, I could go ahead and just call this r squared, and make this 2AR plus 2AR cosine theta, and then divide through. But that becomes 2A plus 2A cosine theta, or 2A 1 plus cosine theta. Okay. That is really easy, and that's basically a cardioid for reasons that we discussed in previous videos. Okay. Well, what if I had taken the plus or minus, okay? Because that would have basically broken this apart into r squared minus 2AR cosine theta, and I would have basically had a negative 2AR on this side. Okay, well that would have basically just boiled down to r is equal to 2a, and then it would have been basically this negative right here. It would have been negative 1 plus cosine theta. Okay, well let's look at both of those graphs. Okay, so we have, and let's just use a value for a. Let's use 2. So how about 2 plus 2 cosine theta, which oddly enough I think was actually the one that was in there before I just erased it, plus 2 cosine theta. Okay, let's go to the window and make sure that we have enough room. Let's go ahead and go from, let's go negative 5 to 5, and negative 5 to 5 by 1s, and then, okay, did I mess up the window? Okay, did I, graph, window range. Oh, I know what I did. Okay, I put a negative 5, negative 5. The x-min is less than the x quit. Oh, that's because I did it too early. Okay, so point, 0, 5. This is negative 5 to 5, step down by 1. Okay, yeah, I just put them in the wrong spot. Okay, there's the first one. There's R1. Oh my gosh, will you look at that? It's tracing right over it. It just starts at a different place, okay? And that's why you don't have to do the plus or minus, because these basically are equivalent. Those two are equivalent graphs. They just start at different points. So, alrighty, let's go the other way. Okay, well, how about 3 secant theta is equal to r? Well, I know that I need, let's go ahead and multiply both sides by cosine. Oh my gosh, that's just x is equal to 3. How wonderful. Okay, well this tangent down here, I know that tangent is sine over cosine. And you can also, remember that in our original, and basically its tangent is equal to y over x. Well, tangent is equal to y over x because tangent is sine over cosine, and it's also r sine over r cosine, which transfers into y over x. Okay, so you can do, if you don't remember this one, you just take tangent and you turn it into sine over cosine, and then go r, and it becomes y over x is equal to 2, or y is equal to 2x. Okay? And if you think about it, that should make sense as to why it looks like a linear that goes through the origin, because basically all it's doing is it's giving you a tangent ratio of opposite over adjacent. But, all right, let's go ahead and move on to another one. Now, if we have r is equal to 2 cosine theta plus 2 sine theta, what can we do from there? Well, the sine theta and the cosine theta don't have an r next to them. Oh gosh, I wish that cosine and sine had an r next to them. Okay, so I do so. Let's just multiply through by r. And I get 2r cosine theta plus 2r sine theta. And now I have it exactly in the form that I need it to. And that had the benefit of taking r and turning it into r squared. So this becomes x squared plus y squared is equal to 2x plus 2y. And I get x squared minus 2x plus y squared minus 2y is equal to 0. That is a conic section. Not only is that a conic section, it's a circle, okay, with radius of square root of 2 and center at 1, 1, okay? Now, this one right here, this is a little bit trickier, okay? Now, what I'm going to do is I'm like, oh, well, if I want to get sine by itself, or if I want to basically get rid of the plus pi over 4, I have to use my sum and difference identity. So I get r is equal to, let's take the 2 out and let's just deal with this. Becomes sine theta cosine pi over 4 plus cosine theta sine pi over 4. And of course, both of these are root 2 over 2. And root 2 over 2 is actually, when you sort of unrationalize the denominator, is 1 over root 2. And if you want to pull out that 1 over root 2, you get 2 over root 2, which is just root 2. So this simplifies down to that. And then it looks a whole lot like this one up here, but instead of having a coefficient of 2, I simply have a coefficient of root 2. And so I get r squared is equal to root 2 r sine theta plus r cosine theta. When I multiply both sides by r, I get x squared plus y squared is equal to root 2y plus root 2x. And it winds up looking remarkably similar to the one above. I just have a different coefficient. I have root 2 instead of 2. Now, and that all of this should seem really, really familiar. I just wanted to run through a couple of examples just to sort of refresh that memory. It has been a while since that we've seen it. Okay. I'm going to go ahead and call this video to a close. In the next video, we were going to talk about derivatives and tangent lines in polar. And that'll be a whole lot of fun, so be on the lookout for that. If you have any questions, please do shoot me an email. Bye.